All right. Well, welcome to Lecture 7 on General Relativity, although we are not technically a General Relativity yet. We're still in the midst of Special Relativity here at the moment. And my goal in this lecture is to summarize kinematics and dynamics and how they're modified by Special Relativity, at least a little bit of it. I mean, I think you could do a whole course in these things, really. So we're just going to scratch, I would say scratch the surface in some sense. All right, so let me just get into it. So we're in four-dimensional flat space, so-called Minkowski space, right? And you want to talk about physics. So when you study introductory physics, what you learn is that you have to, define observables, and the observables we study are typically what? Position, velocity, acceleration, momentum, maybe kinetic energy, so forth, potential energy, your forces, and so forth. But in special relativity, of course, there's time and space. And so, like, if you want to describe physics in a proper special relativistic sense, you need to describe things in terms of space-time. So what that means is that you're not just going to talk about position, you're going to talk about, like, for example, space and time. Time-space, I suppose. So your position is a 4-vector, right? And so I'm going to use the notation in this lecture, and this is notation that was used in my general relativity class I had with Dr. Kafitz. He liked to use like a upper bar for a 4-vector. So this would be a contravariant tensor, I suppose. And this dot product is the Minkowski product, like we talked about before. I don't know if I use this notation yet. I might not even use this notation after this lecture, but for this lecture I'm going to use this notation. And anyway, so there's that. And so basically you've got the time piece, and then over here you've got the Euclidean dot product making the end of it. All right. You can talk about the square of a 4-vector. That gives you this. And the square of a 4-vector is an invariant. Now this much we can say: if the square of a 4-vector is less than 0, it's time-like. If it's equal to 0, it's light-like. If it's positive, it's space-like. If you can parameterize the path I shouldn't say that. If I should say you can parameterize the path of a particle with mass, all right, using its so-called proper time. So the proper time is the time which is ticking on a clock on the particle, which moves with it. It's so-called co-moving frame. And so the time in the co-moving frame is the proper time. And so you can parameterize the path of something using the proper time. That's often called a world line, which isn't to say it's a line. It could be something else, all right? There's interesting world lines that are hyperbolas, for example. Anyway, so here's the deal. You got your ds squared, which is the invariant interval. You can write the differentials of time and space like that. If you think about this, in the rest frame, you're not moving, right? You're co-moving, so you're not changing your distance. So all that's left is the proper time. So ds squared is minus c squared d tau squared in the rest frame, which gives you that, and that's an invariant. All right, so apparently the proper time is also something we can talk about in the same sense we can talk about ds squared. And okay, so anyway, when we solve for d tau squared, we get this, but we could also cipher from that various relations between the derivative of proper time with respect to the time of some other frame and the velocity of the particle in question with respect to that frame. In particular, we get that d tau dt is the square root of 1 minus u squared over c squared. This is exactly 1 over gamma. Remember, gamma is the reciprocal of this thing. Gamma is a function of u. Okay, so that's where we're starting. Now, I've got a lot of these. This lecture is largely taken from a particular book that I have, and although I think that the things in this lecture also were pretty much in my general relativity course, I don't have the book right on me. Maybe I'll go get it when we get a little bit further into this lecture here. I'm going to keep going on here for now. So the gamma of u is 1 over the square root of 1 minus u squared over c squared. All right, that's dt, d tau dt, all right? And, or you could say dt d tau is gamma. All right, so that so far we've just talked about the space-time analog of the position vector, which is the, well, like the space-time, the world line, all right? Now, if you differentiate the world line with respect to proper time, that gives you what's known as the 4 velocity. So 4 velocity is a little bit different than regular velocity. You can do the chain rule on the 4 velocity, change your taus to t's, and when you do that, you end up with a gamma times this guy right here. So you see the 4 velocity actually is related to the ordinary velocity we know from previous work in physics by a multiplication by gamma. 4 velocity is a 4 vector, right? So it's got 2 pieces. The one piece is gamma times the speed of light. The other piece is gamma times the ordinary velocity, where gamma is 1 over the square root of 1 minus u squared over c squared. Here, this u squared is the magnitude of the velocity. And of course, here we're describing the 4 velocity with respect to a particular frame of reference, an inertial frame, I suppose. Now, notice that the 4 velocity dot the 4 velocity is an invariant. To be more precise, this is u lower, like this is u upper nu, u lower nu. It's a contraction across an upper and lower index. It's an invariant. You can prove that this is the same value at any Lorenz, in any 2 different frames of reference that are related by an inertial, a Lorenz transformation rather. And anyway, so you can also calculate it. It's minus gamma squared c squared plus gamma squared u dot u. And what's that? Well, that's gamma squared times u squared minus c squared, which is this, which by algebra is that, multiplying by c squared over c squared, yeah? And that's minus 1. Hey, look at that. So the dot product, well, not the dot product, the Minkowski product of the 4 velocity with itself is minus c squared. Of course, this is an invariant. That's just a number, independent of your choice of frame. So the 4 velocity has this invariant no matter what value, no matter what inertial frame we choose to describe the 4 velocity in. So what else can we talk about? Well, we can also talk about 4 acceleration. What's the 4 acceleration? So the 4 acceleration is the space-time generalization of acceleration, and you can describe it by the proper time derivative of the 4 velocity, or you could describe it as the second proper time derivative of the world line. All right, and it's got 4 components again. Yeah. Excuse me, I'll sip my coffee here. So it's got 4 components, and again, my apologies if the crickets are too loud tonight. Eventually the winter will be here, and then they'll be quiet, and then I'll be really cold. But anyway, so the 4 acceleration is, the proper time derivative of the 4 velocity, which, by the way, is gamma using the chain rule, trading a proper time derivative for just a plain old time derivative. So the plain old time derivative is taken with respect to a frame of reference, which is not necessarily the co-moving frame. All right, it's just an arbitrary frame that we're measuring the velocity of this particle in. And anyway, so we have gamma du bar dt, which, again, u is gamma c, gamma u. So you differentiate these things. You got a product rule to worry about here, right? And you've got speed of light. You can pull that out, of course. And well, we get this. Now the thing is, the du dt, that's the derivative of the ordinary velocity with respect to the ordinary time. That's just plain old acceleration. That's the second time derivative with respect to t. of the spatial part of the world line. And you've also got this u d gamma dt term in there. All right, again, where we were introducing gamma being, that quantity. Here, a again is du dt, which is the second ordinary time derivative of the spatial part of the world line, where I'm using x vector for x, y, z in this particular part of my notes. Now, I should mention the instantaneous rest frame of the particle has u equals to 0, which means gamma is equal to 1. So if you look at that, you see that a bar, the 4 acceleration, is just 0a, where a is the just plain old acceleration in the rest frame. And you can notice that the invariant interval, the square of the 4 acceleration, or a bar dot a bar, is equal to 0, only if a is the ordinary acceleration that it experiences in its own rest frame is equal to 0. Great. I'm sure if I was a better physicist, I'd have something profound to say right here, but I'm not. So anyway, so theorem: the 4 velocity and the 4 acceleration are perpendicular in the sense of the Minkowski product. All right, like it says there. And so to get that, you just differentiate what we already know, which is that the Minkowski product of u with itself is minus c squared. So if you differentiate that with respect to proper time and use the so I guess I've never proved this. That that would be a good homework problem for you guys to do, because pretty much anytime you have a product which is bilinear, if you compose the bilinear product with functions of time and you differentiate, you're going to get this kind of product rule with respect to the product. The same thing happens for the Euclidean dot product and the host of other. The same thing happens for the cross product as well. If you differentiate a cross product of vector functions of time, vector valued functions of time. There's also a product rule. There's a product rule for pretty much any product that has that bilinear property. Anyway, so there's a product rule here, and that's lovely because then the symmetry of the Minkowski product allows me to repackage that as 2u bar dot du bar d tau, which is just say that u dot a is equal to 0, which is the claim there. Now, these relations would be very useful if you were really trying to solve a problem, a specific applied problem in the context of special relativistic dynamics or kinematics, let's say. These invariant quantities are terribly useful because no matter what frame of reference you're using, that's something that you can hang your hat on. That u bar dot a bar is equal to 0, whatever frame of reference you choose to formulate the physics. So continuing the 4 acceleration, here's a theorem. If the 4 acceleration has its spatial component, temporal component, a sub up 0, and then let's call it script a vector, all right, the spatial part of the 4 acceleration, then you can show that the temporal component is the ordinary velocity dot the spatial part of the acceleration over c, and the spatial part of the spatial it's spatial. Sorry, I'm an idiot. The space part of the 4 acceleration, it's gamma squared times the ordinary acceleration plus gamma to the power 4 of the velocity dot the ordinary acceleration over c squared times the velocity. Now this, that's I have no intuition for what on earth is going on here. I will just say that that's a weird formula. I mean, I prove it down here, great. It's not hard to prove, but like, what is this? I'll admit, I do not personally have an intuition for that at the moment. My bad, but now, so here's the ordinary velocity, and here's the ordinary acceleration. I should be careful. Later in this very lecture, I will use the double dot notation for the derivative with respect to proper time. So don't assume that this forever in this lecture means time derivative. I will later use the double dot notation for proper time derivative, so watch me on that, okay? Anyway, so from 3, the last page, we already had this relation from the basically product rule. And so if you take the dot product of this bad boy right here, and when I say dot product, I mean Minkowski product of that with A, you get this, which we know is 0 from our previous work. And so that's equal to minus C gamma A0. And this is the dot product of the spatial part of the 4 velocity and the spatial part of the acceleration. There's a gamma because there's a gamma in the spatial part of the 4 velocity, remember, here? So that picks up the gamma there. And then, but there's a gamma on both pieces, so they cancel out when you solve for A sub 0 and you get U dot A over C. Lovely, that's half of the theorem here. Then, the other part, it's a little bit sneaky. So, let me see if I can get it all into frame here. Maybe. Yeah, maybe we do. So, gamma d gamma dt is 1/2 ddt of gamma squared. If you've done a lot of classical mechanics, you'll recognize this trick. This is the calculation we do to, like, see the kinetic energy pop out of a term where it's kind of not there. This is the kinetic energy chain rule trick. And so I get 1/2 ddt of gamma squared by the chain rule in reverse here. And then gamma squared is literally that. So you differentiate that thing. It's a reciprocal function, so that's minus 1 over the thing inside the function squared times the derivative of the thing being reciprocated, which is over here. U squared is u dot u after all. And then you got to do the product rule on this thing, which gives you derivative of 1, 0. Derivative of this is all this jazz. You know, du dt dot u plus u dot du dt, lovely. And you still got this minus 1 over c squared riding along over here. So that 1 over c squared, come out here, there's a gamma to the 4th because we've got, this is the square root of all that stuff to the 4th power. That's where the gamma to the 4th comes from. It's just this term right here. And this, there's 2 of them. Symmetry of this is the ordinary garden variety calculus 3 dot product of 3 vectors. So that's commutative. You can combine these. You get a 2 from this. You get that 2 from there. Those 2's cancel. The minuses cancel, and out pops this 1 over c squared gamma to the 4th u dot a. Then you take this thing, plug it back up in here, right here, or as my neighbor in North Carolina used to say, right here. Actually, I can't do the mountain North Carolina accent justice. There's no y'all. It's Ewans, and there's a variety of other, you know, special Appalachian sayings that are special to that part of Appalachia. But anyway, so there it is. There's the formula for the spatial part of the 4 acceleration. Let me go on. It's not terribly the big point of this lecture or anything. It's just these are just some fun calculations, all right? Now, one of the homework problems I gave you was to derive the velocity transformation rules. Here's a really cool alternative way to derive them using the 4 velocity. All right, so the 4 velocity gamma c, gamma u vector, right, which you could, you know, more detail, gamma c, gamma u1, gamma u2, gamma u3. For some reason, this lecture is making me think of Yo Gabba Gabba. If you remember the Yo Gabba Gabba. I was just talking about that the other day. Daniel used to watch Yo Gabba Gabba when he was a little guy. Anyway, I think he turned out okay. So, so look at this. The interesting thing is this is equal to u sub 0. That's equal to u sub 1. That's equal to big U sub upper 2 and big U upper 3, rather. So if you look at that, you can write the ordinary velocity as the ratio of the first and the 0th 4 velocity components. You can write the ordinary second velocity as the ratio of the second and the 0th 4 velocity components, and you can write the third velocity, ordinary velocity, as the ratio of the third and the 0th 4 velocity. Now I should be more careful here. These should be all upper 0, upper 1. I'm not being careful here. It's a bad influence of the book I was looking at, which I now feel obligated to go grab. Give me a minute here. I wish this camera had a pause function. It does not. Sorry for the delay. I'm back. So, coffee. Coffee gotten cold too. All right, so this book right here, Dynamics and Relativity by W.D. McComb, is more or less what I've been following for the start of this. It's a nice book. It's got, you know, fairly careful, like, regular classical mechanics, and then I've been kind of picking and choosing what I want from chapters 12 and 13 and 14 for this lecture. So I wouldn't say I'm following this book directly, but it is a nice book which is somewhat centered around the idea of this lecture, the later chapters anyway. However, one of the faults of that book in some sense is that it doesn't adhere to the index notation conventions, like the upper index notation, because it is much more of a math book, let's say, than a physics book. And so it's a so I'm blaming the book for me not putting my... See, I realized my sin here. I started putting U upper 0 and U upper 1. You see that? But up here I slipped. And I guess I could fix it, but I don't have an orange marker. I'm going to move on. We have more important things to worry about. You get my point. These are just typos. Got it? Okay. But here's the neat thing. Once you write the ordinary velocity in terms of these 4 velocities, then you have a straightforward path towards changing the formula by changing a frame of reference, because we know how a 4-vector transforms under a Lorenz transformation. In particular, if we do an x boost by velocity v, and I meant big V here, all right? But my apologies, like big V and little v, it's the same V, all right? So like there's a V, and it's equal to big V in this page, okay? Don't try to distinguish those. All right. And well, you do need to distinguish those between the little u. Little u is the velocity of the particle in question. Here v is the velocity of a frame, moving frame of reference with respect to the original frame that we were using here. So we're starting by characterizing the velocity of a particle in some frame of reference, and we're saying, okay, take another frame of reference which is moving in the x direction with respect to the original frame, right, the so-called x boost. Then the question is, how do the velocities of the particle compare in the original frame versus the boosted frame? So we'll use primes for the boosted frame, and here's the Lorenz transformations. All right, we talked about those before. And so what's the velocity? What's the velocity in the boosted frame? Well, u1 prime is going to be the ratio of the boosted 4 velocities, which is just this. The gamma v's cancel, and you do the math here. Some gamma, and these are gamma. These are all gamma sub u's, gamma of u's. All right, gamma, 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 gamma. Those cancel, and they leave you with u1 prime is u1 minus v over 1 minus v u1 over c squared. That's the velocity transformation. And then now if you instead asked, so sometimes we give the velocity of the moving particle in the boosted frame. If you do that, then the Lorenz transformations have a plus instead of a minus, and you end up with a plus here instead of a minus. So beware, sometimes you see the reverse. Sometimes you see the reverse transformations and there's a plus here. Don't read too much into it. It's really just whether you have, you know, the velocity of the ball moving on the train, or you have the velocity of the ball moving with respect to the, you know, the landscape as your starting point. So it's not a terribly deep difference, the plus versus the minus. But anyway, I go on. And then when you take the ratio of like the U2, and as you can see, I feel increasingly guilty for writing this up too here, so much that I've corrected it down here at this point. All right, so I take the ratio. This time I can't cancel the gamma because I don't have a gamma. Let's see. I don't end up being. I can't cancel the gamma of V down here because I've only got one of them. So it survives, and you get this formula. So, and then if you that is the reciprocal of a reciprocal, so you can write it upstairs. So the velocity transformation in the transverse direction, transverse velocity times the square root of 1 minus the boosted speed squared over c squared divided by 1 minus speed of the moving frame, speed of the particle divided by c squared. And if this is true for the second spatial direction, of course it's true for the third spatial direction, because x2 and x3 are pretty much the same. There's a symmetry between those. They're both unboosted, and they have the same sort of geometric relation to the direction which was boosted, which was x. But anyway, you can contrast how I derived it right here, which I would say is in some sense more rigorous, to the kind of ad hoc differential calculation I gave you in the homework. They finds the same formulas, right? And the algebra is almost the same, but this is, I think, more logical because, the formulas here, you're finding a way to characterize the velocity in terms of the four velocity in such a way you can do it for any frame. So if you can do it for any frame, you can compare two frames, which is kind of nice. I do feel like there is a more complete derivation based on a careful application of the chain rule, switching from time to proper time. I've not been successful to get through that in this particular semester. I've tried in previous semesters, and I always get lost in the notation. Anyway, let me not turn this into a loss. It's a win. I found it better. I mean, that calculation I showed you on page 5 is from McComb's book, and I'm grateful for it. It's a really good way to think about it. So anyway, for momentum, next on the agenda here, which is the momentum's four-dimensional analog. And so what you're going to do is mass times the four velocity. Now here, this mass is, I will sometimes later call it m sub 0. All right, let me just say that. My m is equal to m sub 0. And this is sometimes called the rest mass. It's important to emphasize that, because in some of the older books, like for example this one, Resnick, this is a wonderful book, by the way. This is like a really useful book. There's a lot in this book, I think, that any introductory student of special relativity would gain much from carefully studying this book, for sure. But it does have some sort of antiquated ideas. One of them being that when he talks about mass, he talk about the so-called quote-unquote relativistic mass. And for him, the mass, it's this right here. See here? M equals to m sub 0 divided by square root of 1 minus u squared over c squared. So his mass is it's got a velocity dependence in it. So he talks about mass as a function of velocity, which is really an antiquated notion. Mass is an invariant. It is not a function of velocity. It is a fundamental characteristic of the particle you're talking about, just like spin or charge or something else. So we're going to let gamma do all the talking in terms of the velocity relation. So rather than lumping the gamma into the m, we're going to write gamma explicitly and let the m be the rest mass. The advantage of the advantage of doing what Resnick does is it allows him to make the special relativistic formulas look even more like they're really just classical mechanics, but you've replaced the constant mass with a variable mass that depends on velocity. That's kind of the idea, and you can get a long way with that, but let's not do that. So mass is the rest mass. All right, enough of that. So m times 4 velocity, which is, c gamma spatial velocity, which then gives you m gamma c. or MC gamma. MC gamma. There's a joke there, I think. Anyway, so maybe not for your generation. I don't know what is your generation, but depends on who you are, I guess. The velocity, the spatial part here, m gamma u, that is what I would typically call the relativistic. This is relativistic momentum. So it's got ordinary velocity times gamma times m, the rest mass. That's what the relativistic momentum is. P is the relativistic momentum. So the form momentum, it's got m gamma c paired with the relativistic momentum. So what is this? What is this time component of the form momentum about anyway, right? Well, let's investigate. All right. So if we, and I should mention that one of the fundamental principles of relativistic dynamics is the conservation of form momentum. And so that's going to give you two things. Number one, it's going to give you conservation of the the temporal part of the form momentum before and after. And also separately, you're going to have the conservation of the spatial parts of the form momentum before and after. In other words, relativistic momentum would be conserved, and whatever this is conserved. All right. So what is number one? Well, let's think about it. Let's break it down. For u approximately 0, we have gamma approximately 1, and so then 1 is just looking like the conservation of mass. See, because it just says, I mean, m is equal, sum of the m's before is equal to sum of the m's after. So that's just conservation of mass. And let's see here. So for general u, we can expand the gamma in a series, a Taylor series, I guess Maclaurin series. And so this is the binomial series, I suppose. So what you get is you get mc squared for your first term, and you get this when the dust settles here, you get 1/2 m u squared. Well, that's just plain old kinetic energy from classical mechanics, and this is apparently something new. It's what we call, well, this is the rest energy. You notice that when this formula has gamma equals to 1, it just becomes mc squared. So in retrospect, we see that if we took the temporal components of the form momentum and we multiply them by c, what we've got is energy. So in fact, this leads us to define the relativistic energy as m gamma c squared. This is the relativistic energy for a massive particle. And in view of that, number one is nothing more than the conservation of relativistic energy. And I should mention, in general, a particle with relativistic energy E and relativistic momentum P has form momentum P bar equals to E over C comma P. And this relation right here still makes sense when the mass is 0. So like when you have light, you have energy, you have momentum, but you can't write m gamma c squared reasonably. And for light, other things come into play, like the energy is equal to the Planck's constant times the frequency. I don't think I have much more to say about that. Maybe you'll explore some of that in your homework. Basically, what I was thinking about for homework and this part of the course is there's some really nice examples in Macomb, which I intend to convert into homework problems for you guys. That way you can actually experience some decent word problems in the world of relativistic relativistic dynamics. So here's a theorem. E squared is c squared p squared plus m squared c to the fourth. All right, where E is the relativistic energy and p squared is the square of the relativistic momentum, m is the rest mass, and gamma is, well, what it usually is. And so the proof of this is really just based on the invariance of the form momentum square under the Minkowski product. Because when you calculate the square of the form momentum with respect to the Minkowski product, you get minus m squared gamma squared c squared plus p dot p, right? And that's true in all frames of reference. However, if you think about the rest frame, in the rest frame we have relativistic momentum 0, we have gamma equals to 1, and so this formula simplifies to just minus m squared c squared in the rest frame. But this is an invariant, so this in any frame has to be equal to that in the rest frame, and consequently we have the following identity, that you know, and this is, by the way, E over C squared. So you've got E over C minus E over C squared plus P squared equals to minus M squared C squared, and then solving that for E squared gives you the claimed theorem. Now, I hope you saw it. Like, this idea for the proof of this theorem, this is how you do problems in relativistic dynamics. You think about what you're trying to show. You pick a proper 4 vector that describes the physics you're interested in, and then you look at its invariant. You can look at its invariant square. That gives you something, like I said, you can hang your hat on, independent of frame. And then often there's a special frame. Sometimes it's the rest frame, sometimes it's something else. Other problems, like the center of mass frame for a collision problem, is interesting. Or maybe the laboratory frame is interesting. There's some frame where you can simplify your thought process for the problem, and then you can find the value of the invariant specifically for that frame. But then the thing is, that invariant is equal for all possible frames. So that allows you to relate the variables in an arbitrary frame to the very specific value you found in your special frame. In this case, it was the rest frame. So, you know, I think we must have done a half dozen problems in my special relativity course using this idea. Anyway, so for massless particles, we have form momentum is E over C P, and we have that P dot P is 0 because it's a light-like. So it's massless, it's light-like. Its form velocity, its form momentum square is 0, and in fact E is equal to PC for a massless particle. Again, I don't have too much to say about that in this lecture. This much we can say also. Elastic collision of two particles has Lorenz invariant, form momentum 1 dot form momentum 2. So if you've got two particles colliding elastically, then the form momentum before is equal to the form momentum after. All right, because elastic means that both energy and momentum is conserved, and so the so the form momentum before and the form momentum after are going to be equal, the sum of them. But that means you can look at the square of the before and the square of the after, and you also know that the square of P1 is going to be equal to the square of P1 in the after, and likewise for the P2. So you're just left with the invariance of P1 dot P2 and P1 prime dot P2 prime. So that is actually very helpful for solving a particular collision problem. Again, maybe I'll put it in your homework if I get to it, or if I don't think it's too much for you guys. So, all right, so we've talked about position, velocity, acceleration, momentum, right? What's up next? Force, the 4 force. So the 4 force, a couple different things going on here. K sub I, little k sub I, is the relativistic 3 force. It could be defined as dp dt, where this is the relativistic 3 momentum, and that's just garden variety time, right? Now, that is part of a 4 force, k upper alpha, which you can define as the proper time derivative of the 4 momentum. And so that is the proper time derivative of the mass times the 4 velocity. And that is equal to gamma u times 1 over c dE dt, comma k sub I. I don't think this is obvious yet. I think that's derived down here. This is the so-called relativistic 4 force. So, well, well, I'm thinking. I guess this makes sense. I mean, so this is fine. You just got to go back and think about what is momentum. Momentum is E over C, right? E over C, comma P, right? So when you take the derivative if you take a proper time derivative, you can trade it for a regular time derivative, right? Times gamma by the chain rule between t and tau. So this gamma is the chain rule, and then ddt of E over c, well, that's just this. And ddt of p is the k sub I, all right? This gamma is coming because we're switching from a tau derivative to a t derivative, all right? It matters. And what I'm running through right here is from Resnick's book around page 124. So he's like, he doesn't use the little k, he uses, like, the little k is from the McComb book, the F is from Resnick. So this be the force on the mass m naught with velocity u. Newton's law is given by dp dt is ddt of the relativistic momentum, right? And so we can do the product rule, and we also know that, and here's some kind of sneaky move here, we also know that the question is, what's this d gamma dt? You know, that's, what do you do with that? All right, so fine. E is equal to m naught gamma c squared, so dE dt is this. All right, so d gamma dt is something like dE dt, but dE dt is also the change in kinetic energy per time, because we're talking about a free particle here. There's no, like, potential energy or anything, all right? And so dE dt is dk dt, but that's the time derivative of the integral. It's the time derivative of the work done. This is work energy theorem. And then by calculus, you can pull the f out and just multiply that as f dot dl dt, but that's exactly u, so you've got f dot u. So this is that old thing in classical mechanics that the force dot the velocity is the power, right? And so there you go, you get m naught c squared d gamma dt equals to f dot u. And putting it all together, we've got dp dt is the force, and the force has two pieces. It's got f dot u over c squared plus m0 gamma du dt. Now this is kind of familiar. This looks like ma. This is weird. This is a part of the force is in the direction of the velocity. Okay, like that's weird. And there it is. So you can also solve this for, if you solve this for acceleration, you get this formula, which doesn't quite comport. It doesn't quite look like the acceleration formula I got earlier in this lecture, just differentiating velocity, right? The earlier thing I did, let me bring it back here. Bring it back. I'll find it eventually. The thing I did much earlier in this lecture was back on page 4 here, this thing, right? Look at this. So, like, what exactly is the interplay between this so this is the formula for the spatial part of the 4 acceleration, versus here's just a straight formula for just the acceleration. The acceleration as it's related to the force in view of relativistic Newton's law. You know, what's the interplay between those two equations? I'm not sure exactly what to say, but anyway. So this bugged me. I felt like it was inconsistent for a time, and then it finally dawned on me that what Resnick is saying, which is here, like the top line is what Resnick is saying essentially. Well, Resnick is really just saying dp dt is equal to f. He just says that mostly, and then these are like Resnick's calculations, right? And then McComb is saying these things, and I'm like, what's happening? Why is there a gamma in the one but not in the other? Kind of. And I figured that out. It's not that complicated, actually. It's just because one is talking about tau derivatives, the other one's talking about t derivatives. Because dt d tau is gamma, we can say dp dt is dp d tau dt, which is 1 over gamma dp d tau. So what that means is that dp d tau is gamma of u dp dt, which is, by the way, gamma of uf. So when you look at the tau derivative of the relativistic momentum, you get gamma times the force, all right? Which is what you see popping up in here. The tau derivative of the 4 momentum is gamma times the force, all right? Whereas if you just look at dp dt equals 2f, it doesn't seem like there's a gamma here. I mean, yes, there's a gamma inside that derivative, but it doesn't seem like it's the gamma's not multiplicative here, is it? And yet it's multiplicative here. So, like, what's the deal? Well, the deal is that you're doing a time derivative versus a proper time derivative. They are different. They're related, but they are different. Watch out for that. That is the source of much of my confusion early on anyway. Okay, so then here's a question. Here's an example. Now, this example is special to me because this example is the reason I didn't pass my qualifier at the PhD level when I went to physics graduate school. If I had solved this problem correctly, I would have had the qualifiers behind me. I wouldn't have had to worry about those at least. And so what I did wrong, well, I'll explain to you. So here's the problem. You've got a uniform magnetic field into the page, all right? It's pointing down in there. You've got a charge, Q, that's moving this way, perpendicular to the field, right? So the right-hand rule, let me turn my page, if you don't mind, for my convenience. So the right-hand rule says you point your hand in the direction of the velocity, like this, curl your fingers up into the direction of the magnetic field, like at the camera. That means the force is going to be going that way. Oh, man, son of a gun. Oh, into the page. So I'll get it eventually. So I direct fingers into the direction of velocity, and then I curl my fingers into the page. There you dummy, into the page. And that makes us have a force which goes that way. So, you know, the right-hand rule for the Lorenz force law dictates that we get a force which is like that, and then what that's going to do is bend the trajectory up, right? And so, like, what happens is, of course, you get one of these deals, right? Whee! A circle. Well, it was supposed to be a circle. All right, so the charge goes in a circle due to the magnetic field. This is really cool because then you can measure the radius of such tracks, and you can gain all kinds of information about, like, the charge and the mass of the charge and all this stuff. All right, great. So, you know, since these things are perpendicular, Q U cross B is just QUB, and that's equal to, you know, M0 gamma A, because the formula that we had on page 8, the F dot U term is gone because notice that F is perpendicular to U, so that F dot U term is 0. And it just leaves you with the M0 gamma A term. But this is going in a circle, right? So a circle has acceleration as v squared over r. And so then you can solve this for the radius, and there you have it. The radius is M0 U over QB times the square root of 1 minus U squared over C squared. Now, on my qualifier, I didn't know about this. I didn't know about this gamma. I didn't know about this gamma modification here. And so I missed that, and that made me get half credit. And hey, it's part of what brought me back to math, so it's a good thing. But it has been some 20 years since I got that problem wrong, and I feel like I've finally addressed the issue in this lecture. So woohoo! Anyway, if you look at page 128 of Resnick, he actually has experimental results that verify. The experimental results which verified this formula, and in so doing showed that relativistic dynamics as governed by the laws I've been showing you are actually, like, legit. So these formulas here on page, what I say, 128. Here, I'll show you for giggles. So these are the results of Bucherer's, I guess. He's got so if you measure these quantities and let's see here, it says the first column gives the measured speeds in terms of the fraction of the speed of light. Second column gives the ratio of E over m computed with E over m as U over Ib. It is clear that the value of E over m varies with the speed of the electrons. And the third column gives the calculated value of E of that over m equals to, which are seen to be constant. All right. Now, keep in mind the m is the that's his m includes the m naught, But anyway, you can look this up if you want. But so it's one of the the presence of the gamma in the cyclotron, the circular relativistic speed circular motion in the presence of a magnetic field. It's one of the things that verified experimentally that we're on the right track here with this relativistic dynamics stuff. So let me flip the page here. So what I do on the next couple final pages here is just work through that more carefully. I'll try to go somewhat faster this because I'm almost out of time here at the moment. So we've got, Q, U cross B is dp dt. This is the force is equal to dp dt. And the thing is, you get, d gamma dtu plus m 0 gamma du dt. But if you think about this, it must be that d gamma dt is 0 because it's otherwise impossible to have this equation. See, this is perpendicular to u. This is parallel to u. The only way that can be like simpatico is for that to be 0. So it forces us to have d gamma dt is 0, which means that I can bring the gamma inside the derivative without consequence, right? Because it's a constant with respect to time in this problem. So I got ddt of gamma u, which is pretty slick, And then if I take this equation, I multiply by gamma, I get q gamma u cross b is m naught gamma ddt of gamma u. But then what do? Then I notice that this is really the spatial part of the 4 velocity, and that's the spatial part of the 4 velocity, and I'm trading my time derivative for tau derivative. See, now I've got du d tau, and I've got u. Oh, this is nice. Now I've got my u is dx, the world line d tau, and and over here I've got the second derivative of the world line with respect to the proper time. And here's where I warned you about at the start of the lecture, my other use of double dot notation here. So working it out, we've actually got this is our differential equation that we have to solve, which gives you this, all right, so I'm going to go faster now. This is the easy math part, which gives you this and that, all right. And so if I let Vy be y dot, then I've got Vy double dot plus alpha squared Vy. My alpha is QB over m naught. That is a well-known second-order differential equation which we can solve with a sine or a cosine. I use a sine. And here my alpha is the same alpha as that. Tau, phi is just a constant, a is a constant. Okay, so there's my solution. But I know that x double dot is alpha y dot is equal to, well, y dot is literally a sine of that. And so I can integrate this thing once, integrate again, get that. Apply some initial conditions for my convenience, putting C1, C2, and C3 be 0. And so when I look at my x and my y, and so my x and y are both like sine and cosine with a number up front, so you square them, and you just get a squared over alpha squared. You identify that circular motion where the radius is a over alpha. But then if you go back and look what a is the x velocity, which is the original velocity of the charge at time 0. And so you get r is u naught over alpha. And so, but remember that that's the 4 velocity, which is related to the ordinary velocity by the gamma, which then gets us back to the formula r equals to m naught u naught over qb square root of 1 minus u naught squared over c squared. So this derivation was necessary if you don't do the jump that I did about 5 minutes ago. The jump I did, the sneaky trick I did, which I did not justify, it was unjustified, is right there. I said, oh, it's circular motion. Like, it's obviously circular motion. So circular motion has a equals v squared over r. Okay, but I didn't prove this was circular motion. I just, it's like, oh, it's obviously circular motion, right? Is it obvious? I don't know. I guess it is. It's certainly obvious if you do all the math. And so if you do the math, yeah, it's circular motion, and there's the radius. And of course, you could be more careful here. I've neglected to talk about the z-coordinate. I mean, if you understand the math here, you can solve a host of related problems when when the initial velocity of the charge isn't quite lining up the way it did at the start of my picture here. But anyway, that's why the gamma is there. And yeah, if I had a time machine, if I wasn't like violating causality and all that, I could go back and tell myself before I took the qualifier, put a gamma in there, and then maybe, who knows, maybe I'd be a physicist. I don't know. Anyway, thanks guys.